Question 2. The speed of plate movement ranges from approximately 2 to 12 centimeters per year, and the temperature in the upper mantle averages 1,200 degrees Celsius. Attention! How can the plate at such a slow speed not melt inside the mantle over such a long period and not shatter into small pieces under such pressure? Because their theory suggests that the plates sink into depths of 700 kilometers, which would take hundreds of millions of years. Question 3. The plates are believed to subduct into the mantle at angles between 30 degrees and 90 degrees. I mean, according to this theory, the plate would be bent at these angles. However, a plate cannot withstand even minor bending without deformation. Look, the entire ocean floor is covered with fractures, indicating the brittleness of the plate. Therefore, during subduction, series of cracks tens of kilometers wide should have appeared. Where are they? These cracks have not been found in the subduction zone areas. Question 4. Every layer inside the Earth is moving. There is plate motion, mantle motion, and core motion. The core in particular rotates faster than all other layers of the Earth. There is a regularity. The further a layer is from the core, the slower its movement speed. As you already know, plates move at a rate of 2 to 12 centimeters per year. The mantle, which is closer to the core, moves faster than the Earth's crust. This means that any end of the plate, for whatever reason submerged into the mantle, would be torn off by the mantle's flow. But it doesn't break off, because it's just not there. Question 5. The lengths of mid-ocean ridges where the crust is accreted significantly exceeds the lengths of subduction zones, where excess plate material supposedly crawls in. So what does this imply? More crust accretes than crawls into the subduction zones? There are many more similar inconsistencies and unanswered questions. Moreover, 60 years ago, scientists perfectly understood that the subduction theory and lithospheric plate tectonics in general were entirely untenable. Thousands of scientists from various countries wrote about this, relying on the empirical experience of geologists and geophysicists from all over the world. Nevertheless, the erroneous theory was imposed and artificially propagated as the dominant theory. Similarly, faulty theories regarding climate change are being imposed now. Do you wonder where that extra part of the plate which doesn't subduct and has never subducted into the mantle actually goes? Nowhere. The Earth is expanding in volume, and while it used to expand slowly, now it's happening rapidly. That's right. Imagine our Earth was once as small as Mars, but over hundreds of millions of years it grew to its present size. There are numerous works by eminent scientists based on a vast amount of scientific evidence that support this. But we will talk about this next time, if we have an opportunity. Now, let's go back to deep focus earthquakes. What's actually happening there? At the boundary of the continental and oceanic plates, their vibrations are more intense than in the middle of the plate. This is why earthquakes occur at the plate boundaries. During an earthquake, energy is released. Some of it propagates through the plate itself, some of it goes into the atmosphere, and some goes into the mantle. Although it's a small force, constant jolts deform the mantle, heat it up, and liquefy it. So the more regular earthquakes we observe in the Earth's crust, the more favorable conditions are created in these areas for the formation of deep focus earthquakes. Seismotopography reveals the difference in the movement of acoustic velocities at the boundary between the hotter liquid and the colder viscous mantle, as well as deep focus earthquakes caused by the collision of slightly colder and hotter magma streams. The thermal contrast occurs primarily because hot magma, superheated by the core, is currently rising from the Earth's interior. Today, as Earth enters the cycle of external cosmic influence, additional energy is reaching the Earth's core, which turns into heat and warms the mantle. But the problem is that now, unlike in previous cycles, this energy is not dissipated from the mantle as it should. This is happening because the ocean has stopped performing its cooling function. It can be compared to an overheated nuclear reactor when its cooling unit breaks down. The temperature of the mantle magma has been stable for billions of years. If the magma temperature drops even by a degree or a degree and a half, especially in the lower layers, the mantle will start solidifying. However, the magma temperature has begun to rise now. As a result, the mantle, which in previous cycles had only been slightly melting from heating of the core, started melting with a record speed in this cycle. Magma near the core has become extremely hot and fluid, rapidly eroding the mantle and creating new paths within it like holes in cheese. As a result, ducts begin to form in the mantle itself in zones of increased melting. They're like caves in the mountains that are eroded by underground rivers winding inside the mountains. The shape of the caves is determined by how well the rocks inside the mountain dissolve. Similarly, magma dissolves the mantle unevenly due to the difference in the malleability of the substances. As a result, new magma streams started to develop in certain parts of the mantle, and because the magma temperature and consequently the mantle temperature is increasing, the magma becomes more fluid and the number of magma streams increases rapidly. Due to the sudden acceleration of the Earth's rotation in 1995, the centrifugal forces began to push red-hot liquid magma from the core towards the crust. As a result, this magma began to rapidly ascend through the new magma channels. Magma at great depth is pressurized by the layers of the Earth's crust and can be compared to a compressed spring. When magma rapidly melts its way up and descends, it expands in volume because there is less pressure on it from the rocks as it moves higher. This means that magma can straighten out like a spring, thus dramatically increasing in volume. This rise and expansion of magma occurs abruptly, so the movement of hot magma occurs at high speeds. When the hot magma ascends higher, it meets a stream of colder magma, because the closer to the crust, the colder it becomes. The temperature difference between them can be just a few degrees, but it is enough to form magma flows of different temperatures heading towards each other. Some new magmatic rivers approach directly under the very plate. This is what we observe in Siberia. After magmatic rivers transfer their heat to the plates, they cool down and descend. And when the descending river of magma meets the ascending red-hot river coming from the core, their collision leads to what we call cavitation explosions. These powerful cavitation explosions release gases. The cause of the explosion is actual nuclear reactions that release enormous amounts of energy. It would be more accurate to call it an intramantle nuclear explosion. However, we call these explosions in the mantle cavitation explosions only because of the associative similarity. It is these explosions that are being registered as deep focus earthquakes. The greater the contrast in temperature, velocity, and pressure between the colliding magma rivers, the greater the explosion.